These slides are going to be a little rougher. I've been working on trying to create something sensible here. So you might not even ever hear this recording. We'll see. I'm also going to use a couple of videos from YouTube that just do a far better job of visualizations than I can do in the time that I have. So we'll supplement this with YouTube. The goal here is to check on our predictions and also to talk about how does exponential growth connect to all this flattening of the curve thing. On all kinds of websites, you see that graphic, flatten the curve, flatten the curve. Never before has a mathematical graph appeared on so many websites. So I want to connect all this to the numbers we're talking about and what it means. So let's just jump into it. So in the last lesson, which was created before in the middle of spring break, I had made some predictions, and those predictions were wrong. So the predictions on deaths in the US based on the regression model for the 25th, the 26th, and 27th were these numbers, and they were actually higher than that. And so I've been updating my spreadsheet like a decent mathematician, and I've got a different growth factor. So remember that this number is my growth factor. So you can write equations for this, and we did it last time. We can also just multiply from day to day. So a growth factor of 1.25 means you take the number from one day and you multiply by that number to get the next day. You could skip days by just multiplying by it twice, and we'll see some examples. So it turns out that I end up with this slightly different number, which would be a 24.1% increase each day. And so if I put those in, I'm making some new predictions. So this is tomorrow for me, and so maybe this is the day you're viewing the lesson. So I'm making a prediction based on when I made these slides that there will be 3,258 deaths. In fact, we'll look at Wildometer in just a second here. The Wednesday prediction, 5,000, and then Friday, 7,700. So this popped over to Worldometers. So right now, this is Sunday the 29th, and we're at 2,328. And so, seems perfectly reasonable. So if I were to do the arithmetic for that, right? If I took, let's see, if I took my growth factor, I don't know why I can't. There we go. Oops. So let's take this growth factor and multiply by 2328. I get 2889. How does that compare? So it's already a little lower, depending on what we have. It's tough to say. These numbers are updating constantly. They're based on states and municipalities around the country updating when they have time. And it's an interesting thing trying to create lessons around this, because every day I make these, there's a fluctuation and it changes. Again, going back to disaggregating, this is disaggregated data. It's disaggregated by country. And we can see that the US has blown past Italy in total cases. It's past Italy in total number of new cases, and it's lagging behind in total deaths. So let's take a brief detour into this data. Does that mean we should congratulate ourselves? Not yet. Because we were behind Italy, in the sense that Italy's outbreak started before ours. And so look at these serious cases. We're catching up with them in serious cases. So what might happen, hopefully it doesn't. We hope for the best. But a lot of these cases, these new cases that are happening faster in the US now than in Italy, these are cases that have recently been diagnosed. What's going to happen over the course of the illness? How many of these people are going to die? This is very sad. So this number here could change very quickly and probably will change very suddenly, which is what exponential growth does, right? Initially, you have little changes, and then terrifyingly, it takes off very quickly. So we can go ahead and, right, these exponential, the total cases are pure exponential, daily new cases. This is potentially promising. We'll revisit this to talk about exponential logistic growth. Total deaths are still look very exponential. So you would expect, I mean, here's a worst case scenario. You went from 1,000 to, my computer is super slow right now. 1,000, you can look at it doubling here. Doubling took like 4 days. So you could very well expect that by the middle of this coming week that there are 4,000 or 4,500. This is pure exponential growth, and it's alarming. Okay, back to these slides. So here are some predictions. Now again, this is not a very sophisticated way of predicting these numbers, but it's a 101 class, and we're doing our best. So I made this prediction, this slide on the 27th. So there's 3 days. So multiply by the growth rate 3 times to find Monday. Monday to Wednesday, I multiply by twice, exponent of 2. Wednesday to Friday, I multiply by twice. So this is the current growth rate as I have it. All right. Okay. So now checking in on Maine, as of the 27th, there's 168 confirmed cases. Initially I had a growth factor of 1.388. That's a 38.8% daily growth. So it's anything over 1 is the percentage. Monday of spring break was 0. The Friday, I don't know why this T was 9. Oh, it should be 11, sorry. So that would be 11. And then, so I'd over-predicted. This was an overly negative, negative in not in a math way, but in a pessimistic way. So this wasn't very accurate. But that's to be expected. So revising things, right? Friday 327, 168, and then Monday the 16th, T was 0, so Friday is 11 days later. So if we go through the process of calculating that growth factor, just using 2 points. So this is, again, a poor estimate, but it's an estimate. We end up with this growth factor. So again, we calculate the cases now, the cases then, 1 over how many days, and then we take that as an exponent. 1.253, 25.3% increase each day. So here are some predictions for Maine, and hopefully these are wrong. Hopefully the social distancing is working. Hopefully all the measures in place are working. And in fact, if they're working, we expect this number to dwindle until it gets to 1, which is no growth at all. So here are some predictions for the coming week. We'll revisit this and see how they're doing in the next lesson. So this is a comic I found on the net. It's by Comic XKCD. They have funny, nerdy comics. And so they're extrapolating from 2 data points. All right, yesterday there's no husbands. Today there's 1. You can make a line between those 2 points and then project. You can extrapolate extra. So kind of predicting. And then, you know, the stick figure says by late next month you'll have over 4 dozen husbands. So this is obviously ridiculous. The growth can't go on forever. Presumably this is the last, or maybe there's a couple more. But it wouldn't make sense to continue to connect these dots. Well, that's kind of the same for exponential growth. It can't go on forever. There aren't enough people. At some point, the exponential growth has a population of infected people that's larger than the number of people on the planet. So that's just the start of the pandemic. it spreads exponentially initially. Now, several things happen to prevent that. So as people become infected, some of them recover. They can no longer be infected, or some of them pass away, and they can't be infected either. So that reduces the number of people left to infect. Infection occurs through contact, and contact can be eliminated or eliminated through current practices. That can affect the growth. And then the other government recommendations or policies can further lessen the growth factor. The growth factor is malleable. So let's look at this graphically. All right. This green curve here, this is what's going to happen eventually. So initially, the curve is exponential, right up until B, more or less. We don't know where we are on this curve right now. We don't know if we're still here in exponential growth. The top of this curve is not fixed. It depends on what we do. It could be lower, it could be higher. What this curve is are the total number of cases. Right? So the total number of cases that happens in the world or in the country or in Maine is not a number that's fixed in time. It depends on what sort of actions we take, what behaviors do we as a society do to limit the number of cases. Now, the steepest point on this curve is B. This is where this green curve is the steepest, where we're gathering new cases the fastest. The growth factor tells us the steepness at any given time along this curve. So it could be 1.25 here, 1.26, 1.27 maybe, and then it would start to shrink, 1.24, 1.23, 1.18, and so on and so forth, until here it's 1. The growth factor is 1 up here. There is no change. The number of cases here is 100% of what it was here. There's no change. This gray curve down here, this is the rate of infection. So how many people are being affected per day? Sort of a new cases kind of thing. This is a hump. This is the flatten the curve thing we hear about. So this would be the peak rate of infection, when people are getting affected as fast as possible. This is where there's the danger of overwhelming facilities. We go to the, oops, I didn't mean to do that. I forgot that I linked it. Yep. So back to present. We'll go to a dynamic simulation in a moment. So notice what happens between these two pictures. In the second picture, the green curve is less steep. So I've already mentioned before that the growth factor is not fixed in time. It depends on interactions. It depends on quarantines. So if people are quarantining, if people are staying home, if they're limiting their interactions, the infections accumulate more slowly, the green curve is less steep, and the gray curve becomes flatter. If you've taken calculus, the gray curve is the derivative of the green curve. And the biggest point, the highest point on this hill, this gray curve, is the steepest point on the green curve. So this is the sort of thing that a student at the end of Calculus 1 could do. All right? So if we distance, then our exponential growth factor is less, which means our infection rate is less, and that flattens the curve. Now, this curve, this green curve, is called the logistic curve. It's initially exponential, but then it flattens off with time. And we can play around with it a little bit. R is roughly the rate of infection. It's related to it. And so if the rate of infection is higher, right, then it gets steeper. And you can also have more cases. So let me change the axes here. So without getting into how this works algebraically, where this green curve ends up is also a matter of our actions as well. But this R, This is related to that growth factor that we're calculating. And if R is less, if it's not spreading as fast because of our actions and our distancing, this is what's happening, right? It does mean that it'll take longer to reach saturation, to reach that maximum number of cases, but it means that there's more time to deal with those cases. You're going to see this done really nicely in some of the videos that follow this video on Top Hat. And we'll ask some questions, and I'll wrap up the Top Hat lesson with a bit of a conversation about those resources. So for the time being, let's see. Yeah, kind of putting it all together. Let's present this last slide, and I know this is a little longer video. So here's the punchline, and this will be illustrated with some of the YouTube videos. If we're not contagious, when not presenting symptoms, and if it takes 0 to 12 or 0 to 14 days for 95% of cases to present, then spending several weeks in lockdown allows folks to present and not interact with others and be tested and be quarantined so they don't infect others. If others practice social distancing and hand washing, then these lower the growth rate. This can lower the overall number of cases and flatten the curve to allow hospitals, medical personnel, and industry to keep up with demand and supply better treatment. This will lower the mortality rate. So these numbers and these graphs kind of all come together. And we'll continue to revisit this as the semester goes on. My goal here is that by the end of the semester, you can kind of read these articles and really be informed mathematically at a deeper level than the writing is presenting. All right, I will stop there.